Good afternoon, everybody. We are just getting set up. I just want to let everybody know we are here for the Colorado Ready Mix Concrete Association Tech Tuesdays. I am JT Mesite. I'm with Colorado Ready Mix Concrete Association, and I do have Zach Ballard here that will be presenting on performance engineered concrete mixes. So I appreciate all of you attending. Just a couple cleanup items just to start off. First and foremost, we are recording this presentation. This will be posted afterwards here in the next couple days to YouTube for your accessibility and to share with your clients as well. And to all those that registered, I will be sending a follow-up email to all of you with that link, as well as a PDF version of the presentation as well for your reference. So with that, I do want to reiterate that this is a CRMCA hosted event. So we want to make sure that everybody is understanding that we do follow our antitrust regulations within our association. We want to follow all of those antitrust laws, making sure that it is vital that we're conducting this meeting in the manner as respectful to everybody. Understand there are potentially sensitive topics that could be brought up. Zach is going to be talking about, in general, the mixed designs, but there could be individual products that could be brought up. Obviously, we are not trying to sell any individual product, and we are going to be as general as possible with that. With that in mind, understand we're not talking about those products. We're not talking about the cost of those products or the cost of the processes that could be coming into play that affect our members. So just be aware that we are going to hold to that conversation throughout the meeting. So with that, if you do want to become members of the CRMCA, understand that there are many benefits within the CRMCA membership in Colorado, from legislation to education to the CTAC program, testing, adherence, collaboration, and also making sure that we're all really on the same page and we're fighting for the same things in legislature through DOT, and really making sure that the industry is better. And so if you want to be, if you're not members of the CRMCA and you'd like to be, we welcome you to come to our website at crmca.org and join through the membership app on member benefits. And if you are members and just want to get more involved on the technical side with Tech Tuesdays or other aspects of the technical side of the association, don't hesitate to reach out to me as well directly. I run the technical committee through the CRMCA, so I'm welcome to get you guys involved. So with that, we are here talking about Tech Tuesday, and this is a regular series that we've put on starting last year. We have several YouTube videos, both in English and Spanish now, on YouTube with our presentations. We started this year last month, talking about how to utilize the Tech Tuesday series with your clients. I think it was a great information, and Cal Smith from Loveland did explain a lot of that very well, I believe. So if you do want to get sponsor and be recognized during Tech Tuesdays throughout this series, you can click on or scan that QR code that's on the screen. That will be available at the end of the presentation as well if you want to sponsor our series. But as for that, I'm going to pass it over to Zach, let him introduce himself and really get rolling on talking about performance engineered mixes, not just here in Colorado, but everywhere. So, Zach, it is all you.
Perfect. Thank you, JT. Appreciate how you guys having me on and allowing me to give the presentation here. If we have questions as we go on, please feel free to add those into the chat or kind of the Q&A section on there. We'll try and keep an eye on those and address those as they come up. Just don't want to get to the end of the presentation and have questions get passed up or forgotten or something like that, and do the best we can to address those as we go along. So as JT said, my name is Zach Ballard. I work with CTL Thompson. I am the materials department manager here, so I handle all of our concrete cementitious material type projects. And we can get started on the presentation and what are performance engineered concrete mixes. So we're going to use the acronym PECM a bit because performance engineered concrete mixes is quite a mouthful as we go through, but just know that that's what we're talking about with that acronym. So performance engineered concrete mix is a concrete mix design that is specifically tailored and optimized to meet defined performance requirements rather than simply following traditional mix ratios based on strength alone. So PECMs are developed through a comprehensive understanding of specific needs of a project, such as durability, workability, strength, and sustainability. Unlike conventional concrete mixes, which often focus on basic characteristics like compressive strength and standard proportions of cement, water, and aggregates. PECMs are designed to achieve specific outcomes such as enhanced durability, resistance to environmental conditions like freeze-thaw cycles, chemical attacks, etc., optimized workability, ease of mixing, transporting, placing concrete, cost efficiency, achieving the desired performance while minimizing material usage, and sustainability, using alternative materials like recycled aggregates, supplementary cementitious materials, reducing carbon footprint. PECMs are created using advanced mix design methods that take into account both the material properties and the performance criteria for specific construction applications. And I should note that I do mention sustainability here, but we do have a presentation coming up next month on sustainability that will dive into more of that particular part of the work. So we're going to leave that mostly out of the discussion on this particular presentation. So we'll start with the traditional concrete mix design. So we're taking generally one of these, adding to it, two of these, adding to it, three of these, water to get slump, and we get concrete. So we also have our traditional mix design of ACI 211, which is selecting proportions for normal density and high density concrete as a guide. This generally goes through a maximum water cement ratio with minimum cementitious materials, air content, slump, nominal max aggregate size, and strength. So ACI 211, we're going to go over a real quick kind of basic introductory of how that mix design process goes. And the first step is our choice of slump. If slump's not specified, a value appropriate for the work can be selected from table 5.3.1 in the document. Those values apply to concrete produced without a water-reducing admixture. And these slumps range anywhere from 1 inch to 5 inches. Our second step here is choice of nominal maximum aggregate size. Generally, the nominal maximum aggregate size should be the largest that is economically available, consistent with dimensions of the structure. Now, understand that most of the suppliers, we don't really have the choice of choosing many different options here, but we may have a couple of options. So our third step is the estimation of mixing water and air content. So for this example, we're going to do the line here highlighted, the 3 to 4 inch slump with a 3/4 inch aggregate. That's giving us a starting water of 340 pounds per cubic yard. We then go to the next table in ACI 211. This gives us adjustments that we can use in rounded aggregates, increase or decreases in air content. We can kind of go through this chart and adjust our mixing water content based on the properties of the materials that we're working with. For this example, we're not going to do any of those, but know that that's available to us. Step 4 is the selection of our water cement ratio. The required water cement ratio is determined not only by strength requirements, but also factors such as durability. Because different aggregates and cementitious materials may produce different strengths at the same water cement ratio, it's desirable to have or develop the relationship between strength and water cement ratio for the materials to be used. So our example here, we're going to do a 5,000 PSI concrete, non-air entrained. So that gives us a starting water cement ratio of 0.48. Our step 5 is the calculation of the cementitious materials content. So we're going to take that 340 pounds of water, we're going to divide it by our water cement ratio, and we get a starting cement content of 708 pounds. The quantity of cementitious materials per unit volume of concrete is fixed by the determinations made in steps 3 and 4. The required cementitious materials, we divide that out. If, however, we have a specification that includes a separate minimum limit on cementitious materials, in addition to the requirements for strength and durability, the mixture should be based on whichever criterion leads to the larger quantity of cementitious materials. So our step 6, estimation of coarse aggregate content. Aggregates of essentially the same nominal maximum size and grading will produce concrete of satisfactory workability when particular volume of coarse aggregate on an oven dry rotted basis is used in a per unit volume of concrete. The appropriate values for this aggregate volume are given in table 5.3.6. Bulk volume of an aggregate needed, we're going to use that 3/4. This is our value is multiplied by 27, converted to a dry unit weight, multiplying by a bulk volume. We're then going to convert that to an equivalent SSD weight by multiplying by 1 plus the absorption. So we use these values here, 0.64. So all of that put together, we use our 84 pounds per cubic yard, pounds per cubic foot, multiplied by 27. Multiplied by that 0.64, multiplied by a factor for our absorption, gives us our starting aggregate content for our mix. This is in pounds per cubic yard now. Our step 7 is our estimation of the fine aggregate content. So at the completion of step 6, the weights of all the ingredients of the concrete mixture have been estimated, except the weight of the fine aggregate. Calculating the required quantity of the fine aggregate involves use of the volumes displaced by the other ingredients. In concrete, the volume occupied by any ingredient is equal to its weight divided by the density of that material, latter being product of the density of water and specific gravity of the material. For this calculation, the total volume displaced by the known ingredients, the mixing water, the air, cementitious materials, coarse aggregate is subtracted from the unit volume of concrete, 27 cubic feet, to obtain the required number of cubic feet of fine aggregate. So I saved some of our math here, and our total volume of the materials, subtract from 27, equals our required volume of sand is 1,170 in this particular case. So our step 8 is our design weight summary. So we have cement at 708, water at 340, coarse aggregate at 1645, and the fine aggregate at 1,170. And that's the mix design we take to the lab. Then we need to do it 2 more times at varying water cement ratios to develop a 3-point curve. Shown here, using a 3-point curve, we can then pull out a design water cement ratio, interpolate the mixture proportions for our design mix. That looks like as we come across from our design strength till we hit our strength curve, drop that down to our water cement ratio at the bottom, and we can interpolate our values for a design mix. So this is a typical ACI 301 mixture proportioning per ACI 211. This was all started in the early 1990s. The first ACI 211 proportioning document was actually published in 1991 to give an idea of where we're starting and where we're going with this. Some other ACI 211 resources that we have. I don't want it to sound like the ACI 211 proportioning isn't still valid or the methodology is bad. It's still very useful. And we have a host of other documents that we can use there as well. So we have our no slump proportioning, our high density heavyweight proportioning. We have a pumpable concrete proportioning document, a proportioning evaluation document, assessing aggregate gradations, an aggregate packing model, and proportioning with ground limestone and mineral fillers. I guess I should also mention with this that lightweight aggregates and proportioning is in ACI 213 and ASTM C330. So our shift towards performance engineered mixes. We have a demand for improved durability. Modern infrastructure projects require concrete mixtures that can withstand harsh environmental conditions, such as freeze-thaw cycles, aggressive chemicals, high temperatures. Traditional mix designs didn't often provide the necessary durability. Performance engineered mixes focuses on engineering concrete with properties like higher resistance to corrosion, reduced permeability, improved long-term performance in various environmental conditions. We have sustainability goals. The construction industry has increasingly moved towards sustainable practices. PECMs allow for the use of alternative materials, industrial byproducts, fly ash, slag, silica fume, etc., that reduce environmental footprint of concrete production. These materials help reduce the overall carbon footprint, energy use, and waste generated during construction. We have technological advancements. Advances in concrete testing and modeling have made it easier to predict how different mixtures will perform in real-world conditions. Computational tools and mixed and performance-based testing methods allow engineers to design concrete mixes tailored to specific project needs, leading to the creation of more effective and efficient mixtures. Customization for specific applications. Performance engineered mixtures allow for these customizations to meet the exact requirements of a specific project. For example, performance engineered mix could be tailored for high strength requirements, rapid curing times, improved workability, depending on the project's unique demands. This shift enables the construction of a more specialized structures with enhanced functionality. Our cost efficiency, optimizing for performance rather than relying on the standard mix designs can lead to savings in both material and maintenance costs over the life of the structure. Industry standards and regulations. Changes in building codes and regulations have pushed the industry towards a more performance-based approach. As codes and standards become more stringent, especially with regard to environmental and durability concerns, performance engineered concrete mixtures provide a way to meet these requirements while also ensuring that the concrete structures perform optimally over time. Focus on long-term performance. There's an increasing emphasis on the life cycle performance of concrete structures. Instead of focusing solely on initial cost or ease of mixing, the industry has shifted towards designing concrete mixtures that perform better over the life of the structure, reducing the need for repairs and replacements. PECMs aligns with this trend by ensuring that concrete mixtures meet long-term performance objectives such as longevity and minimal maintenance. Better understanding of concrete properties. Through extensive research and testing, the construction industry has gained a better understanding of how various materials and admixtures interact to influence concrete properties. This knowledge enables the creation of tailored mixes that achieve desired performance characteristics, such as workability, strength, durability. So we'll go into composition and ingredients. Our cementitious materials. or fillers, fly ash, slag, silica fume, natural pozzolans like clay or calcine shales, ground glass pozzolans, limestone powders, ceramic waste powders, biochars. We've got a lot of different options. We've got aggregates. The importance of aggregate quality, size distribution, and shape in the mix performance. Admixtures, water reducers, high-range water reducers, kind of the low range are retarders, superplasticizers, set accelerators, viscosity modifying admixtures, the list kind of goes on, waterproofing admixtures, pumping aids, etc. And still our old standby, the water cement ratio and its impact on our workability, strength, and durability. So before we delve into kind of different types of materials, we kind of want to discuss a little of our typical batch plant and some of the constraints. So we can see kind of a simplified schematic of a concrete batch plant. We've got powder silos on the left side of the screen. We've got our aggregates on the right side. So many of these plants, I'm sure that many of our suppliers are using, generally have 2 to 3 silos, have 2 to 3 aggregate bins. So we have some constraints that we're also working with here. It would be nice to be able to put 5 to 10 of those powders that we just talked about, or a multiple amount of aggregates in our plant to be able to use these however we want. But that's just not the reality of what we're dealing with. We do have some ability that the little platform above the concrete mixer truck there, I'm sure most of us have been in a situation where we've stood on top of those and loaded mixers with different materials by hand or by small materials, but that's not generally a long-term or sustainable solution for something that we're going to have to do for a couple hundred yards a day. So our cementitious materials, we've got cement and fly ash and blast furnace slag and silica fume and natural pozzolans and ground glass pozzolans, limestone powders, ceramic waste powders, biochars. We have many different options when it comes to powder materials, whether it be from cementitious materials, supplementary cementitious materials, which provide some pozzolanic reaction, and mineral fillers. So our space in the concrete plant certainly cannot accommodate every single one of these, or even a multiple of these. And some of these may not even be available in certain markets. So we may end up with some of our cement industry folks might end up blending some of these materials for us and being able to provide cements that look more like the European model, where instead of having a handful of cements, we may end up with a multitude of cements with different materials blended into each of these. And we're starting to see some of this go on already, where we have our 1T or 1P type cements. But it may not be a real option for many of our plants to have multiples of these options. We also have aggregates. And we've got our well-graded aggregates, our kind of well-distributed size of aggregates. We have poorly graded aggregates. We have gap-graded aggregates. Our gap-graded aggregates is kind of where our traditional concrete mix design tends to live. We have our requirements by ASTM C33 that gives us a certain size range that say, number 67 rock can meet. We have a certain size range that our sands can meet, and generally those two materials put together give us a gap-graded aggregate. Our performance concrete mix designs are going to use more of a well-graded aggregate or a better distribution of aggregate sizes. There's a lot of different research out on how we can combine these materials. One of those being a coarseness factor, workability factor chart, or kind of the Shieldstone workability chart. And this started kind of in the late 1980s or so. James Shilstone revealed a mixture design process based on the proportioning of aggregates using a combined gradation to a proportion of group of sieve sizes that can be categorized as coarse, intermediate, and fine. He designed a chart to proportioning equations from about 20 mixed designs based in Saudi Arabia, and confirmed the chart and equations using aggregates from the Dallas, Texas area. From Shilstone's experiences, he determined the workability can be sufficient in certain areas of the chart, divided the chart into kind of the zones that we have here. We have kind of a zone 1 and a zone 2, zone 3, a zone 4, and a zone 5. So we plot our aggregates based on a coarseness factor and a workability factor. These are generally just materials retained on the 3/8 sieve, a number 8 sieve, and material passing a number 8 sieve, and our cementitious content. So it only uses a handful of factors from those. And our zones give us different qualities about our concrete mix designs. Our zone 1 is supposed to be kind of our gap graded, very little amounts of intermediate aggregates. Our zone 2 is supposed to be our well graded aggregates in kind of what he called an optimal gradation for concrete mixture design. Zone 3's got a large majority of intermediate with a very little coarse aggregate. The zones 4 and 5 correlate to the extreme sandiness and rockiness ends of aggregate gradations. A large focus has been used on multiple regions of zone 2 for certain applications, and many DOTs are using this for our aggregate proportioning in slip-form pavements. However, Shilstone suggested the bottom of zone 2 is kind of best in that zone. Unfortunately, very little testing has actually been published by Shilstone or others to validate this chart. We've got our haystack curve, or a individual percent retained chart. This is a method for evaluating the exact distribution of each sieve size on an individual percent retained. The chart easily shows the excess or lacking of sieve sizes of a combined gradation. From experiences, people have specified a maximum boundary of somewhere in the range of 18 to 22% and a minimum boundary of 5 to 12% retained on each sieve. No real research being conducted to kind of prove those limits, but that's what we found has generally worked. We have kind of our modified from that haystack curve to the tarantula curve. So our tarantula curve is kind of modified, and this was done by Tyler Lay and his team at Oklahoma State. This work has had quite a bit of research done around it. Done around, I believe, 2010 or so, somewhere around in there. We also have our Power 45 curve. This started in the concrete industry in about 1907. It's now used kind of primarily by the asphalt industry. The Power 45 curve uses a combined gradation to a best fit along a straight line, the cumulative percent passing chart. This is done by Fuller and Thompson in 1907. The straight line from the origin to the nominal maximum size has thought to be a maximum density of a combined gradation, which supposedly creates the maximum density and a minimum amount of voids in a mixture. Kind of delve into our chemical admixtures here. We have kind of a traditional view of our chemical admixtures has always been to reduce the water, which makes our concrete stronger, more durable, and overall just more is better, right? But what we're missing here is we're not talking about sticky concrete or potentially slump loss. We have some charts generally by admixture suppliers that show if we have a high range water reducer that's on the left, we get a larger amount of water reduction, but the time that slump stays is not as long. We have some slump controlling admixtures and slump retaining admixtures, but those are generally not going to give us the same high water reduction values. So as we push admixture dosage higher and higher and reducing our water lower and lower, we're going to start to run into some problems. If we hit it at the batch plant, we have high water reduction, slump looks good, but if we have high slump loss, at the job site, we're just going to add a bunch of water right back into it, and we're going to defeat the purpose of having these admixtures and going through this exercise of the performance engineered mixes. So quick background on some of our polycarboxylate ether-based superplasticizers. It's a targeted polymer design. It's to specific concrete properties. The mode of action is based on the adsorption of the polycarboxylate onto a cement grain, dispersion of particles by electrostatic repulsion, and steric hindrance. The polymers consist of backbones with carboxyl groups and side chains. The first component, the backbone with the carboxyl groups, is responsible for the attainable water reduction and initial slump mixing time, kind of respectively. The second one, the side chains, determines the slump keeping capability of the superplasticizer, affected by an increasing number of side chains. The crucial factor is the limited space for these carboxyl groups and the side chains along the backbone. Either a carboxyl group or a side chain can be attached to a certain location. Basic variations in those factors lead to three kind of generic types of polymers, and we get the water reducers, kind of a slump control and slump retaining type polymers that we just had talked about. So we get the adsorption of the polymer, the backbone, onto our cement grain. This detail of that adsorption of the polymer onto the cement grain. The improved workability due to steric hindrance. Steric hindrance is a slowing of a chemical reaction due to what's called steric bulk. It's usually manifested in intermolecular reactions, whereas discussion of steric effects often focus on intermolecular interactions. Steric hindrance often exploited for controlled selectivity, such as slowing unwanted side reactions like crystalline growth from cement hydration. And this is kind of a detailed view, improved workability. It's going to push those two particles apart without having to add water into the space between those. So why is all of this important? Well, we understand the materials that we're working with. We understand the materials we're working with. We can better understand how to make adjustments with those materials for various outcomes. We get key performance indicators, things like compressive strength, flexural strength, modulus of elasticity, durability factors like permeability, shrinkage, freeze-thaw resistance, and our various test methods and standards. We have various ASTM and AASHTO, ACI test methods, including non-destructive test methods. So we can't control what you don't measure. We use compressive strength as an example. We all generally test and track compressive strength. And this can be done and maybe should be done with some other parameters as well, like shrinkage or permeability through surface resistivity or RCP, maybe rheology or stickiness. But our normal distribution of test results gives all of the test results possible depending on a coefficient of variation. So a higher coefficient of variation is going to give us a wider range of results. If we have a tighter coefficient of variation, then we have a narrower group of expected results. Each one of these curves on the screen here is shifted off to the right side of the curve. So our mix is designed for a higher strength than our specified strength. If we can dial our mixes in and our quality control on these mixes, we can actually start to push these to the left and closer to our specified strength. So now we can spend a little bit less on materials potentially. And each one of these curves is still giving us the same failure rate of approximately kind of 5 to maybe 10% failure rate, which we expect we are going to get some low strength values. That's the way a normal distribution of results works. But depending on if we're spending more time and money in quality control, mix design development, we can shift these curves to the left, reducing our over design, which is going to reduce the costs on each of these mixes. We'll go over a quick example. So I pulled these specifications from a particular project that I was working on. We've got design mixtures, and each concrete mixture submit alternative mix designs, characteristics, materials for project conditions, and all the things that the specifications say. Our shrinkage testing per ASTM C157. Maybe not necessarily something that's always tested on our concrete mix designs that are coming out of our producers, but it provides an opportunity for a performance engineered mix. We also have a maximum embodied carbon of the concrete mix, reference drawings for embodied carbon goals. We're not going to get into that part of it, but this is another opportunity for performance engineering mixes. And our strength maturity curves for concrete mixes specified with a 56-day strength design, develop and submit these strength maturity relationships in accordance with ASTM C 10774, extend this maturity testing out to 56 days. So not every supplier has all of these things sitting on the shelf ready to go, but if we have a handful of performance mixes, getting these types of specifications might be a little bit easier. And so further into those specifications, we have a performance and design requirements. We'll focus specifically here on the shrinkage, where we have concrete for slab on grade placed directly on vapor barrier is 0.046%. So as we get into these, we've got some concrete mix design tools that we have at our disposal. So we have various computer-based programs like Stadium, the Concrete Mix Evaluator, Civil Lab. We have applications on our phones. We have various phone apps. We also have AI and machine learning programs. And we have the old standby of kind of the spreadsheet or spreadsheets, depending on how you want to run with it. There's many options out there. This isn't any kind of exhaustive list or recommendation or anything like that. This is just to show that we have lots of options available to us. And honestly, pick one that you like and run with it and work with it. We will use those then to go in and do a design of experiments. So the design of experiments method allows our quality teams to simultaneously investigate multiple potential causes of process variation. So experimental design begins by identifying the major factors that could cause process variance. Designed experiments tool contains 3 elements. For example, we'll use this on the process of making a pizza, and the elements are kind of the following. We have our factors, or controllable and uncontrollable variables. These are the inputs to our process. Factors are considered as either controllable or uncontrollable variables. Factors in the pizza example include the oven, the dough, the sauce, the toppings, etc. We have levels, and this is the settings of each factor. These are the potential settings. The levels in the pizza making process are like the temperature of the oven, cooking time, the amount of sauce and toppings used. And we have our response. This is the output of the experiment. The DOE strives for a measurable output that is influenced by the factors and their differing levels. The response or output from the example is how the pizza tastes. I'm sure you're all wondering how it all relates to concrete, so we'll get back to the original project example, but this is just to show kind of how the design of experience kind of fits and generally what most of us are doing on a day-to-day basis when it comes to working with concrete mix designs and performance engineered mixes. Or back to concrete example. So there's a number of inputs in the process that can affect the output. Factors that are most relevant to the end result are the ones most important to the DOE. These factors are selected by the project team in like a brainstorming session, for instance. In ordinary circumstances where time and budget are finite, which I think is where most of us live, the team should limit experiment to 6, maybe 7 key factors at the most. These factors are controlled by setting them at different levels for each run. So the factors affecting our drying shrinkage, we've got paste content, water cement ratio, cement cementitious content. That's what that's supposed to say there. Our aggregates, our type, our size, our shape. Admixtures, both positive and negative potentially there. So once these factors have been selected, the team must determine the settings at which these factors will be run for the experiment. The example of cooking a pizza demonstrates that some factors are measured in numbers, such as oven temperature, cooking time. Other factors are more qualitative, such as which toppings are used, are measured in categories, converted into coded units for a linear regression analysis. Think compressive strength, shrinkage, things like that for us in the concrete world. The more levels are identified for each factor, the more trials will be required to test these levels. To ensure an optimal number of levels are selected, focus on a range of interest. This range includes settings used for a normal course of operations and also may include settings of a more extreme scenarios. Greater the difference in factor levels, the easier it becomes to measure the variance. So we have high or low water cement ratio. We have how much cement or cementitious content we have, how our aggregate grading can affect these results, and our admixture dosages, water reducers versus shrinkage reducers, and how we're going to use those in the concrete mix design experiment process. So the response is the outcome of the experiment. Outcomes are most helpful in improving the process when they can be measured in quantitative terms rather than qualitative attributes. A response that is quantifiable makes the experiment well suited to additional scrutiny of statistical regression analysis or other mathematical ways of looking at the data. The design of experiments allows those inputs to be changed to determine how they affect the responses. So instead of testing one factor at a time while holding others constant, the DOE reveals how interconnected factors respond over a wide range of values without requiring the testing of all possible values directly. This helps the project team understand the process much more rapidly. So do we have our shrinkage increase? Did we have a shrinkage decrease? Did we have no change? I can tell my experiment chart didn't show up well here, but we're going to take this stuff here, which is no particular brand of a shrinkage reducer, and we're going to go through 3 different dosage ranges, these dosage 1, dosage 2, and dosage 3. And the goal of this is we're going to get 3 different results. We're going to get a result number 1, result number 2, and a result number 3. And for our examples here, we really don't need any particular result, but we're going to go through and we're going to analyze each one of those results. So do we take the lowest result? Well, maybe. Depends on the result, right? If we had results ranging from 0.45 down to maybe 0.30, we really only needed to be below 0.46 in this performance engineered mix. So We may not need to take the absolute lowest value, but we want to be able to evaluate those results, compare it back to what we were looking at in the beginning and what we were after for the performance engineered mix. Can we evaluate multiple variables in this? Yeah, more care needs to be taken in evaluating those experiments when more than one variable is involved. But through careful experiment design and analysis, we can evaluate multiple variables, potentially combinations of shrinkage reducers, aggregate gradations, and potentially water cement ratio. Do we need to redesign the experiment? If we're looking for results that meet a certain criteria and the results didn't meet those, then yes, we will need to redesign the experiment. If there are opportunities to further optimize based on those results, then yes, we'll need to redesign the experiment, change some of those factors and inputs and levels, and rerun and go through this process again. So this is a cyclical process, excuse me. So our applications for performance engineered concrete mixes, different locations, what we can do with these mixes and where we can go. So we have infrastructure projects, which are our bridges, tunnels, highways, and dams. We have our commercial and residential construction, which is our potentially high-rise buildings, parking structures, or even foundations. We also have our specialty projects, some of our airport runways or marine structures, potentially industrial floors. The advantages of our performance engineered mixes: we have tailored solutions for specific needs. So we have the ability to meet unique requirements for various types of projects. Enhanced lifespan of structures. We have improved resistance to wear, environmental conditions. We have better workability and placement, achieving desired consistency and ease of handling in the field. And our cost effectiveness in the long term. So reduction in maintenance and repair costs. We've talked a little bit about these, where this cost efficiency, cost effectiveness, and we're going to get into the challenges of implementation on that. And one of those is going to be that cost potentially. But we do have mixed design complexity as a challenge. We need expertise in creating and testing optimized mixes. We also have material variability that we're dealing with these differences in locally available materials. I think anybody that's made concrete at about any time can say that the materials are never super consistent, and we're always having to work through this material variability. And our initial cost considerations. So we have higher upfront costs due to specialized materials or testing. This is one of the things that could potentially is our upfront cost that maybe we can reduce later through our reduced maintenance, or potentially passing those on to the ownership of the structure, whatever that happens to be. There's also, not to the sustainability portion of it, you've got kind of those the credits that can kind of work in some of the favor around there for projects that can be a benefit as well. And our future construction, we've got performance engineered mixes are paving the way for stronger, more sustainable, and cost-effective concrete solutions. And we've got a little call to action kind of for everybody that we're going to encourage exploration and adoption of performance engineered mixes in upcoming construction projects. So that is kind of assuming that, if you're a ready mix supplier, that you get more than a couple weeks notice that you were awarded a project and have some time to work on some of these. And we can also start getting a leg up on some of the mixes that we're seeing just based on historical, where we are seeing those reductions in global warming potential. We are seeing mixes that now have shrinkage requirements, that have durability requirements, whether they permeability or et cetera. So we can start working on some of these mixes now and work on those projects in the moment so that we've got something in hand to come to the table with these projects and potentially provide a value added service to these projects also. And I realize we went maybe a little bit quick through some of that, but we've got some time for Q&A session here and kind of anything that's come up in the chat. I didn't see anything particular come through at the moment, but I think we do have, let's see.
No questions, but I've opened up the mics for anybody that might have any questions,
perfect.
comments now as well.
Okay. We'll put the next screen up here. So if anybody has anything, go ahead and shout it out at the moment, or we can got some information there on the Tuesday Tech Tuesday series and contact info and everything for CRMCA's updates and events on the screen as well, if anybody's looking for that information also.
All right. Any questions, comments? All right. Well, with that, I'm going to say thank you to Zach for presenting on the performance engineered mixes. I think this is definitely some of that content that I don't think everybody understands straight away, right? To say that it's something that they can transfer over to, but it's obviously something that we can look at, and now we can share a lot of that information of really what that process is to really go through performance engineered mixes and where I think as an industry are going to need to get going towards here in the near future with sustainability still at the forefront of the conversation nationally and globally. So thank you, Zach, very much. Any last minute comments before we end the session?
Hey, sorry.
Go ahead.
I had a quick question. This is Adam with Aurora. Just a quick question about fly ash and cementitious materials versus just mixes with straight cement, 100% cement, and no secondary cementitious. I've heard some people suggest that, fly ash or other SCMs are really, really important, but some suppliers are still using pure cement mixes every day. And I'm curious if, Zach, if you are seeing, data or industry trends moving in one direction or the other. Thanks.
Yeah, no, absolutely. Appreciate the question. When it comes to the SEM usage, we've gone we've seen the whole gamut, right? Where we started out with straight cement only, and then fly ash was kind of slow to develop, and then it started making its way into just about everything, and we that back out just going to a straight cement mix. I will say the durability aspect that we get from having additional SCMs is worth the benefit, in my opinion. The potential to optimize our mixes for different properties is a benefit of having those SCMs. There's also some discussion of whether the current, the power plants that are producing, say, fly ash, and whether they will be able to keep up with demand based on energy requirements and clean air requirements is still kind of to be determined, but that's something that's been going on in the industry here for a little bit as well. We also have new mined materials that are being used as supplementary cementitious as well. I think there's certainly benefit to having SCMs in the mixes. there's really no, I wouldn't think that there's a downside to having a mix without them, but I think that having them in the mix allows us the opportunity to be a more engineered mix and gives us better durability in the long term. They do have a lot of research studies out there that show that it's great for reducing permeability, and that's going to be our biggest factor in longevity. That if this concrete can last longer by having one of these materials in there, then I think that right there is a benefit of itself, that we can have material that lasts longer and our repair costs are lower long term if we have a better, more durable concrete. I hope that answered your question, but if not, I'm happy to clarify.
That's great. Thank you.
Thanks for that question, Adam. Much appreciated. Any other comments or questions now that the ice has been broken? No. All right. Well, with that, Zach, any last minute comments now before we end? Oh, Aaron, you have a question. Go ahead.
Yeah, hey, Aaron was like, thanks. Zach, I was just curious.
Looks like maybe Aaron, did you have a question in there? There was a hand raised on the screen there. Wanted to check on that.
Yeah, can you hear me? Yeah, can you hear me? Hello?
Looks like Zach cannot hear you now all of a sudden.
JT, can you hear me?
I can, yes.
Okay. I can type it in the chat if need be. But no, I was just curious on what he get his take on something.
Yeah, not sure what happened there with Zach, but we definitely lost connection to him apparently there. Zach, can you hear us yet?
I can hear you now. Sorry, did the
okay.
Can you hear me now? Not sure what happened there. Something changed.
Yeah, we did hear you. It did look like you couldn't hear us. So Aaron, go ahead and ask that question.
Yeah, Zach, can you hear me?
Yeah, I can hear you.
Yeah, I just want to get your take on cementless concrete, like what Secrete Technologies is working with, concrete without cement altogether. I mean, do you think I know that's one extreme to like the sustainability, efforts, with all the sustainability stuff happening, I think it's only going to get further along down the rabbit hole. I mean, do you think we're going to go to a situation just like that someday, or what's your take on all that? I know you don't want to get too into sustainable stuff though.
Sure. No, that's it's a great question. So to kind of get into our, cementless or even kind of just different material processes in kind of that cement realm, instead of kind of the traditional clinker process and grinding, that we've got some electrochemical, electrostatic type processes now that are creating different types of cement. And I think it's an interesting process. There's always the question of, I guess, how well we can scale that up. And then if it's scalable to a portion that we can actually start to use it in a volume that makes some kind of impact. I think it would be beneficial if we can get into kind of the sustainability portion of those. But it could be a way that it goes. I think we're very, very much in the infancy of that at this point. But if we're able to make the same, well, I'll kind of say same with a little bit of quotes around it, but the same type concrete with these materials that are going to last as long or longer, with just same durability that we've seen on what I'll call kind of our traditional concrete. I think it could be a way to go into the future, but we're very much in the beginning of that technology at this point.
Sure, completely agree. Thank you.
Yep. Yeah, absolutely. Thanks for the question.
I'll give it a few seconds, see if anybody else would like to ask a question or anything. So third time's the charm, Zach. Last comments?
No, yeah, no real comments or anything from me, but you've got, I guess is just a message to anybody out there. If you guys have questions on any of this, there's lots of resources that CRMCA has that feel free to reach out, and that's what the association and group is here to do for the members, is provide resources. And if anyone is in need of those resources, feel free to reach out. And we can I say we here, but I mean probably passing that buck on maybe, but our folks at CRMCA can get you in touch with the right people and the right resources, and definitely take advantage of what they have to offer.
I appreciate it, Zach. Thank you all for sticking around and listening into what Zach had to offer in regards to performance engineered mixes. And as he said, if you want to keep up with CRMCA's events, we do have the QR code there as well as a QR code for if you are interested in sponsoring the remainder of Tech Tuesday series, which we have one next month, which we actually have a guest speaker from PCI Mountain States and with Jim Schneider going to be presenting on the sustainability of concrete mixes. And then we'll continue the conversation in August with another conversation where we're going to tie in both sustainability and utilizing that in performance engineering mixes as well. And then further in the fall, talk about really the projects, what responsibilities are on projects, and what we can do as not just an industry in concrete, but as a team on projects to have those conversations and make a successful project at the end as well. So with that, thank you. We'll follow up with this information, and we'll continue on, and hopefully we see you all next month. So thank you very much.
Thanks, Zach.
Thank you,
Thanks,
Zach and JT.
Thank you.
Thank you.